So this is a brief lecture, because I'm not here, about the two worksheets you have for the next 2 days. So we're talking about nuclear reactions. The way the worksheets are set up is to read through here and then answer some questions about the reading. So you just go back and forth, read through here, answer some questions using the word fusion and fission. See notes at top actually refers to these notes, honestly. Then in part 3, we're given types of particles, and you're supposed to read through go back and forth between filling this in and trying to figure out what the different particles are. And then finally, use the words decay and capture and finish up the piece. The next day, things suddenly look more complicated. We have these equations, and at the beginning, it is to identify these 3 pieces we had on the first day and the type of reaction that we talked about at the end of the first day, or you read about at the end of the first day, and put those 2 things together so that that's an alpha particle, and then decay is making a product. And then there's a balancing piece, and this is the focus of this lecture, and then putting everything together. And then honors has a little bit more work to do after that. So I was going to go ahead and just give the presentation that I thought I would give before I was called away. So radioactivity is the emission of extra energy, but also of particles that come out. So you'd have this nucleus, because it's a nuclear change that we're talking about. The nucleus changes to something brand new, and we often give off a particle and give off energy during those things. Sorry about my messages. Should have had that say no, no messages. Oh well, so much for technology. Keep going. So the next thing was, where's all this energy come from? Well, it comes from something called the strong force. We have positive protons repelling each other, these 2 positive charges. And we have something called the strong force, which is a very, very, very strong force that holds everything into the nucleus. Once you break that nucleus, you release energy, which could also be called binding energy, because it's the energy holding the nucleus together. And suddenly that release causes a nuclear change. So unstable nuclei are the ones that undergo change. And we talked about when something's unstable, it may have too many or too few neutrons. And the time in which this process may happen is in very short microseconds or very long billions of years. But that nucleus is not stable. Now, some are stable, like carbon-12. All the carbon in your body, the sugar, the muscles, everything is mostly stable. And a tiny, tiny, tiny portion is unstable carbon-14, which when it breaks apart makes nitrogen-14. Okay. There are 3 principal types of radiation. There's alpha, beta, and gamma, and they were named in order of their discovery. Alpha, which is the largest, was discovered first, then beta, and then gamma, and they're all Greek alphabet symbols. So alpha, we write this for alpha, 4He2. We write this for beta, 0E, -1. And we write gamma that's the only thing we write for a gamma ray. This is a gamma. This is actually a helium nucleus. So that's why alpha particle is written like that. This is actually an electron, which is written like this. You will see the beta particle written this way sometimes, but not with the material word covering. And then each of these has a certain amount of energy, with the highest amount of energy here, with the highest amount of energy here, which means it can travel very far, and the minimum energy here, which means that it actually gets stuck in barriers. So if you have an alpha particle, clothing would be enough to stop it. If you had a beta particle, it would go through paper but get stuck in a thicker material or a more dense material, like aluminum foil or wood. And finally, the gamma ray would travel through everything and even through feet of concrete. But if you had several bricks of concrete laid next to each other, you could finally stop a gamma ray, or if you had a very thick piece of lead. So this is the hard part. So sort of rushing to get here so we can focus on what does all this mean? It looks very complicated, and I just don't want you to get too worried about it. So what's happening here is we're going to take these mass numbers and we're going to show that the mass numbers on one side of the equation and the mass numbers on the other side of the equation, the reactants and the products, are the same. So if you add these two together, you get 236, and if you add all these together, you also get 236. And the point is that I want to be able to take this out of the equation and just make it a big X and have you solve for this. And you can see that if I made this X, it wouldn't be a really complicated algebra equation. So despite the complicated format, it's actually supposed to be very simple algebra that you're doing. We do not only the top, but the bottom, where the bottom numbers are also equal on both sides. In this case, it's about charge, because each of these is a proton. That's what the atomic number is equal to. So I have 92 positive charges, and I have 92 positive charges here. And that's because occasionally we'll be using a beta particle, and the beta particle had a -1 for that electron. And so when we use that, it suddenly becomes about charges. It doesn't become just about protons. So that's why it says charge here. Okay, moving on. So how's this work? I give you stuff. So the easiest part to give you is, let's go back one, is the atomic number. So you find nitrogen, and that has that atomic number. You find helium, you find hydrogen, you get the atomic numbers. There are multiple isotopes, so this is not a number off the periodic table. This is a given isotope, which may or may not be off the periodic table. In this case, these are all off the periodic table. Not that one. Yeah, that one too. And then you calculate for what is this going to be. So to do that, we would do 14 plus 4, which you can either write out or you can do it in your head, because all the numbers, even though I'm writing them out, are just right there. So 14 plus 4 is equal to 18. And so 18 is equal to what plus 1? And so my answer is 17. And then repeat that at the bottom. 7 plus 2 is equal to z plus 1. And so that becomes 9 is equal to z plus 1. And that means z is 8. Once we have z is the atomic number, I can use that to find the oxygen off the periodic table. And that's what you do. So this will actually be an answer on the worksheet. So if I ask you to find AXZ, then that's how you find it on the periodic table. So I'm going to put these notes in the module so that you can find them. But I did think that me talking about it would be more helpful. So I'm just going to wrap this up with 4 examples. so we can sort of continue to go over it and make sure that you understand what's happening. So we need that color. Oops. So 1 plus 10 equals 11, and the other side is a plus 4. Oops, I'm showing the answer. Ignore the answer for a second. So 11 is equal to a plus 4, so that means that a is equal to 7, so I'm solving for this. And then b is 5, 0 plus 5 is equal to z plus 2, and then when we solve that we get 3, and then I use the periodic table to find that this is lithium. Okay, so sometimes the math is super easy and sometimes you need to use a little bit more number sense, but it's never going to be different than that. Now, we had talked about that you'd have to learn capture and decay, so I'm just going to talk about that really quick. This is a neutron, and I doubt if you, and this is an alpha particle. And then we have these two terms, capture and decay. And so my memory device is to write C, D, E, right? C, D, E. And that's capture, happens on this side. And then we have the arrow. And decay, and I tried not to use the word emission too many times, but the word emission means the same thing. So decay or emission happens on this side. And then we name the reaction based on what we see. We see a neutron capture. And that would be the name of this process that's happening here. While on the other side, I see alpha decay. Right? So this being created is called alpha decay. So I'm not going to do it again, but those are the two processes. That's the way you figure out emission, decay, capture. Okay, let's do another math equation to show the conservation of mass. Conservation of mass on top, which is, oops, wrong color. Here we go. 222 is equal to a plus 4. So we get 218. And then on the bottom, we have 86 is equal to z plus 2. So that's 84. You look that up on the periodic table and it says Po. And so that's that answer. Again, I can't answer questions, but if you have questions, you can send me a note quickly, through email, and then maybe I can get back in time for this to make sense. So 1 plus 14 equals a plus 1. You don't have to write everything out. Many of you can do this in your head. You should plug it back in to make sure it's okay. So this is the calculation I'll do, and when I solve for a, I get 14. So essentially I can just cancel these two additions out. And then on the bottom, we have that, where there's where the equal sign is, and 7 equals what? Plus 1, 6, and 6 is C. So I solve for that one. And I think by this time you kind of get what's happening. You may need scratch paper to solve for it, but then you write this. So to write this, these values, you need to enter it, right? So in Google Docs, you would do control period, and that would let you do a 7 up high. And then if you did a control comma, that would let you do a 3 down low. And then if you did a control comma again, that would undo the below writing and go back to normal writing, and you could write in, whoops, you could write lithium in. So control dot period raises it up, control comma brings it down, control period comma then returns it to normal writing. If you're using a Mac, instead of using control, you use the command key. That looks like that. Okay. And last one here. Again, if we do this kind of quickly, these two are equal to these two. So 213 equals a plus 4. That was one I felt like. And then subtract the 2 and you get 209. And this one, I can just sort of do that one in my head. That's going to be 80. And 80 equals, oh, I got this wrong before. Go to the periodic table, H2. Okay, and that is the end of my really quick notes. Now I know that didn't cover everything. So just to remind you, you can read through all this, and it's basically how well were you reading things, and you're supposed to remember many of these things for day 2. And then in day 2, this is where you're doing all this, comparing the two sides and making sure they're equal with each other, and writing in here with that control up and control down. I gave you 2 examples each time so that you could see how to do it and also how to write them. And that's it. You get to the end and you're done. So 2 days of nuclear chemistry. Okay, good luck. Let me know if you have any problems.